Part 2, Chapter 10, Recent Comets, Part 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Aaron Carlo in San Clemente, California. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Recent Comets, Part 1. Chapter 10. Recent Comets. On the 2nd of June, 1858, Giambattista Donati discovered at Florence a feeble round nebulosity in the constellation of Leo, about 1/10 the diameter of the full moon. It proved to be a comet approaching the sun, but it changed little in apparent place or brightness for some weeks. The gradual development of a central condensation of light was the first symptom of coming splendor. At Harvard, in the middle of July, a strong stellar nucleus was seen. On August 14th, a tail began to be thrown out. As the comet wanted still over 6 weeks of the time of its perihelion passage, it was obvious that great things might be expected of it. They did not fail of realization. Not before the early days of September was it generally recognized with the naked eye, though it had been detected without a glass at Pulkova, August 19th. But its growth was thenceforward surprisingly rapid, as it swept with accelerated motion under the hindmost foot of the Great Bear and passed the starry locks of Berenice. A sudden leap upward in luster was noticed on September 12th, when the nucleus shone with about the brightness of the pole star, and the tail, notwithstanding large foreshortening, could be traced with the lowest telescopic power over 6 degrees of the sphere. The appendage, however, attained its full development only after perihelion, September 30th, by which time, too, it lay nearly square to the line of sight from the earth. On October 10th, it stretched in a magnificent scimitar-like curve over a third and upwards of the visible hemisphere, representing a real extension in space of 54 million miles. But the most striking view was presented on October 5th, when the brilliant star Arcturus became involved in the brightest part of the tail, and during many hours contributed, its luster undiminished by the interposed nebulous screen, to heighten the grandeur of the most majestic celestial object of which living memories retain the impress. Donati's comet was, according to Admiral Smythe's testimony, outdone as a mere sight object by the great comet of 1811, but what it lacked in splendor it surely made up in grace and variety of what we may call scenic effects. Some of these were no less interesting to the student than impressive to the spectator. At Pulkova, on 16th September, Winnicke, the first director of the Strasbourg Observatory, observed a faint outer envelope resembling a veil of almost evanescent texture flung somewhat widely over the head. Next evening, the first of the secondary tails appeared, possibly as part of the same phenomenon. This was a narrow straight ray forming a tangent to the strong curve of the primary tail and reaching to a still greater distance from the nucleus. It continued faintly visible for about 3 weeks, during part of which time it was seen in duplicate. For from the chief train itself, at a point where its curvature abruptly changed, issued, as if through the rejection of some of its materials, a second beam nearly parallel to the first, the rigid line of which contrasted singularly with the softly diffused and waving aspect of the plume of light from which it sprang. Olber's theory of unequal repulsive forces was never more beautifully illustrated. The triple tail seemed a visible solar analysis of cometary matter. The processes of luminous emanation going on in this body forcibly recalled the observations made on the comets of 1744 and 1835. From the middle of September, the nucleus, estimated by Bond to be under 500 miles in diameter, was the center of action of the most energetic kind. 7 distinct envelopes were detached in succession from the nebulosity surrounding the head, and, after rising towards the sun during periods of from 4 to 7 days, finally cast their material backward to form the right and left branches of the great train. The separation of these by an obscure axis, apparently as black quite close up to the nucleus as the sky, indicated for the tail a hollow cone-like structure, while the repetition of certain spots and rays in the same corresponding situation on one envelope after another served to show that the nucleus, to some local peculiarity of which they were doubtless due, had no proper rotation, but merely shifted sufficiently on an axis to preserve the same aspect towards the sun as it moved round it. This observation of Bond's was strongly confirmatory of Bessel's hypothesis of opposite polarities in such bodies' opposite sides. The protrusion towards the sun on September 25th of a brilliant luminous fan-shaped sector completed the resemblance to Halley's comet. The appearance of the head was now somewhat that of a bat's wing gaslight. There were, however, no oscillations to and fro, such as Bessel had seen and speculated upon in 1835. As the size of the nucleus contracted with approach to perihelion, its intensity augmented. On October 2nd, it outshone Arcturus, and for a week or 10 days was a conspicuous object half an hour after sunset. Its luster, setting aside the light derived from the tail, was at that date 6,300 times what it had been on June 15th, though theoretically, taking into account, that is, only the differences of distance from sun and earth, it should have been only 1/33rd of that amount. Here, it might be thought, was convincing evidence of the comet itself becoming ignited under the growing intensity of the solar radiations. Yet experiments with the polariscope were interpreted in an adverse sense, and Bond's conclusion that the comet sent us virtually unmixed reflected sunshine was generally acquiesced in. It was, nevertheless, negatived by the first application of the spectroscope to these bodies. Very few comets have been so well or so long observed as Donati's. It was visible to the naked eye during 112 days. It was telescopically discernible for 275, the last observation having been made by Mr. William Mann at the Cape of Good Hope, March 4th, 1859. Its course through the heavens combined singularly with the orbital place of the earth to favor curious inspection. The tail, when near its greatest development, lost next to nothing by the effects of perspective, and at the same time lay in a plane sufficiently inclined to the line of sight to enable it to display its exquisite curves to the greatest advantage. Even the weather was, on both sides of the Atlantic, propitious during the period of greatest interest, and the moon as little troublesome as possible. The volume compiled by the younger Bond is a monument to the care and skill with which these advantages were turned to account. Yet this stately apparition marked no turning point in the history of cometary science. By its study, knowledge was indeed materially advanced, but along the old lines. No quick and vivid illumination broke upon its path. Quite insignificant objects, as we have already partly seen, have often proved more vitally instructive. Donati's comet has been identified with no other. Its path is an immensely elongated ellipse, lying in a plane far apart from that of the planetary movements, carrying it at perihelion considerably within the orbit of Venus, and at aphelion out into space to 5½ times the distance from the sun of Neptune. The entire circuit occupies over 2,000 years and is performed in a retrograde direction, or against the order of the signs. Before its next return, about the year 4000 A.D., the enigma of its presence and its purpose may have been to some extent, though we may be sure not completely, penetrated. On June 30th, 1861, the Earth passed, for the second time in the century, through the tail of a great comet. Some of our readers may remember the unexpected disclosure, on the withdrawal of the sun below the horizon on that evening, of an object so remarkable as to challenge universal attention. A golden yellow planetary disk, wrapped in dense nebulosity, shone out while the June twilight of these latitudes was still in its first strength. The number and complexity of the envelopes surrounding the head produced, according to the late Mr. Webb, a magnificent effect. Portions of 6 distinct emanations were traceable. It was as though a number of light, hazy clouds were floating round a miniature full moon. As the sky darkened, the tail emerged to view. Although in brightness and sharpness of definition it could not compete with the display of 1858, its dimensions proved to be extraordinary. It reached upwards beyond the zenith when the head had already set. By some authorities, its extreme length was stated at 118 degrees, and it showed no trace of curvature. Most remarkable, however, was the appearance of 2 widely divergent rays, each pointing towards the head, though cut off from it by sky illumination, of which one was seen by Mr. Webb and both by Mr. Williams at Liverpool a quarter of an hour before midnight. There seems no doubt that Webb's interpretation was the true one, and that these beams were, in fact, the perspective representation of a conical or cylindrical tail hanging closely above our heads, and probably just being lifted up out of our atmosphere. The cometary train was then rapidly receding from the earth, so that the sides of the outspread fan of light shown by it, when we were right in the line of its axis, must have appeared, as they did, to close up in departure. The swiftness with which the visually opened fan shut proved its vicinity, and indeed Mr. Hind's calculation showed that we were not so much near as actually within its fold at that very time. Already Monsieur Liais, from his observations at Rio de Janeiro, June 11th to 14th, and Mr. Tebbutt, by whom the comet was discovered in New South Wales on May 13th, had anticipated such an encounter, while the former subsequently proved that it must have occurred in such a way as to cause an immersion of the earth in cometary matter to a depth of 300,000 miles. The comet then lay between the earth and the sun at a distance of about 14 million miles from the former, its tail stretched outward just along the line of intersection of its own with the terrestrial orbit to an extent of 15 million miles, so that our globe, happening to pass at the time, found itself during some hours involved in the flimsy appendage. No perceptible effects were produced by the meeting. It was known to have occurred by theory alone. A peculiar glare in the sky, thought by some to have distinguished the evening of June 30th, was, at best, inconspicuous. Nor were there any symptoms of unusual electric excitement. The Greenwich instruments were, indeed, disturbed on the following night, but it would be rash to infer that the comet had art or part in their agitation. The perihelion passage of this body occurred June 11th, 1861, and its orbit has been shown by M. Kreutz of Bonn, from a very complete investigation founded on observations extending over nearly a year, to be an ellipse traversed in a period of 409 years. Towards the end of August, 1862, a comet became visible to the naked eye high up in the northern hemisphere, with a nucleus equaling in brightness the lesser stars of the Plough and a feeble tail 20 degrees in length. It thus occupied quite a secondary position among the members of its class. It was, nevertheless, a splendid object in comparison with the telescopic nebulosity discovered by Temple at Marseilles, December 19th, 1865. This, the sole comet of 1866, slipped past perihelion January 11th, without pomp of train or other appendages, and might have seemed hardly worth the trouble of pursuing. Fortunately, This was not the view entertained by observers and computers, since upon the knowledge acquired of the movements of these two bodies has been founded one of the most significant discoveries of modern times. The first of them is now styled the comet 1862-3 of the August meteors, the second 1866-1, that of the November meteors. The steps by which this curious connection came to be ascertained were many, and were taken in succession by a number of individuals. But the final result was reached by Schiaparelli of Milan, and remains deservedly associated with his name. The idea prevalent in the 18th century as to the nature of shooting stars was that they were mere aerial ignis fatui, inflammable vapors accidentally kindled in our atmosphere. But Halley had already entertained the opinion of their cosmical origin, and Chladni in 1794 formally broached the theory that space is filled with minute circulating atoms which, drawn by the Earth's attraction and ignited by friction in its gaseous envelope, produce the luminous effects so frequently witnessed. Acting on his suggestion, Brandes and Betzenberg, two students at the University of Göttingen, began in 1798 to determine the heights of falling stars by simultaneous observations at a distance. They soon found that they move with planetary velocities in the most elevated regions of our atmosphere, and, by the ascertainment of this fact, laid a foundation of distinct knowledge regarding them. Some of the data collected, however, served only to perplex opinion, and even caused Chladni temporarily to renounce his. Many high authorities, headed by Laplace in 1802, declared for the lunar volcanic origin of meteorites. But thought on the subject was turbid, and inquiry seemed only to stir up the mud of ignorance. It needed one of those amazing spectacles at which man assists no longer in abject terror for his own frail fortunes, but with keen curiosity and the vivid expectation of new knowledge, to bring about a clarification. On the night of November 12–13, 1833, a tempest of falling stars broke over the earth. North America bore the brunt of its pelting, from the Gulf of Mexico to Halifax, until daylight with some difficulty put an end to the display. The sky was scored in every direction with shining tracks and illuminated with majestic fireballs. At Boston, the frequency of meteors was estimated to be about half that of flakes of snow in an average snowstorm. Their numbers, while the first fury of their coming lasted, were quite beyond counting, but as it waned a reckoning was attempted from which it was computed, on the basis of that much diminished rate, that 240,000 must have been visible during the 9 hours they continued to fall. Now there was one very remarkable feature common to the innumerable small bodies which traversed, or were consumed, in our atmosphere that night. They all seemed to come from the same part of the sky. Traced backward, their paths were invariably found to converge to a point in the constellation Leo. Moreover, that point travelled with the stars in their nightly round. In other words, it was entirely independent of the Earth and its rotation. It was a point in interplanetary space. The effective perception of this fact amounted to a discovery, as Olmsted and Twining, who had simultaneous ideas on the subject, were the first to realize. Denison Olmsted was then professor of mathematics in Yale College. He showed early in 1834 that the emanation of the showering meteors from a fixed radiant proved their approach to the Earth along nearly parallel lines, appearing to diverge by an effect of perspective, and that those parallel lines must be sections of orbits described by them round the sun and intersecting that of the Earth. For the November phenomenon was now seen to be a periodical one. On the same night of the year 1832, although with less dazzling and universal splendor than in America in 1833, it had been witnessed over great part of Europe and in Arabia. Olmsted accordingly assigned to the cloud of cosmical particles, or comet as he chose to call it, by terrestrial encounters with which he supposed the appearances in question to be produced, a period of about 182 days, its path and narrow ellipse meeting near its farthest end from the sun, the place occupied by the earth on November 12th. Once for all, then, as the result of the starfall of 1833, the study of luminous meteors became an integral part of astronomy. Their membership of the solar system was no longer a theory or a conjecture. It was an established fact. The discovery might be compared to, if it did not transcend in importance, that of the asteroidal group. C'est un nouveau monde planétaire, Arago wrote, qui commence à se révéler à nous. Evidences of periodicity continued to accumulate. It was remembered that Humboldt and Bonpland had been the spectators at Cumana after midnight on November 12, 1799, of a fiery shower little inferior to that of 1833, and reported to have been visible from the equator to Greenland. Moreover, in 1834 and some subsequent years, there were waning repetitions of the display, as if through the gradual thinning out of the meteoric supply. The extreme irregularity of its distribution was noted by Olbers in 1837, who conjectured that we might have to wait until 1867 to see the phenomenon renewed on its former scale of magnificence. This was the first hint of a 33 or 34-year period. The falling stars of November did not alone attract the attention of the learned. Similar appearances were traditionally associated with August 10 by the popular phrase in which they figured as the tears of St. Lawrence. But the association could not be taken on trust from medieval authority. It had to be proved scientifically, and this Quetelet of Brussels succeeded in doing in December 1836. A second meteoric revolving system was thus shown to exist, but its establishment was at once perceived to be fatal to the cosmical cloud hypothesis of Olmsted. For if it be a violation of probability to attribute to one such agglomeration a period of an exact year, or submultiple of a year, it would be plainly absurd to suppose the movements of two or more regulated by such highly artificial conditions. An alternative was proposed by Adolf Erman of Berlin in 1839. No longer in clouds, but in closed rings, he supposed meteoric matter to revolve around the sun. Thus, the mere circumstance of intersection by a meteoric of the terrestrial orbit, without any coincidence of period, would account for the earth meeting some members of the system at each annual passage through the node or point of intersection. This was an important step in advance, yet it decided nothing as to the forms of the orbits of such annular assemblages, nor was it followed up in any direction for a quarter of a century. Hubert A. Newton took up in 1864 the dropped thread of inquiry. The son of a mathematical mother, he attained at the age of 25 to the dignity of Professor of Mathematics in Yale University, and occupied the post until his death in 1896. The diversion of his powers, however, from purely abstract studies stimulated their effective exercise, and constituted him one of the founders of meteoric astronomy. A search through old records carried the November phenomenon back to the year 902 A.D., long distinguished as the Year of the Stars, for in the same night in which Taormina was captured by the Saracens and the cruel Aghlabite tyrant Ibrahim ibn Abed died, by the judgment of God, before Cosenza, stars fell from heaven in such abundance as to amaze and terrify beholders far and near. This was on October 13th, and recurrences were traced down through subsequent centuries, always with a day's delay in about 70 years. It was easy, too, to derive from the dates a cycle of 33¼ years, so that Professor Newton did not hesitate to predict the exhibition of an unusually striking meteoric spectacle on November 13 through 14, 1866. For the astronomical explanation of the phenomena, recourse was had to a method introduced by Erman of computing meteoric orbits. It was found, however, that conspicuous recurrences every 33 or 34 years could be explained on the supposition of 5 widely different periods, combined with varying degrees of extension in the revolving group. Professor Newton himself gave the preference to the shortest of 354.5 days, but indicated the means of deciding with certainty upon the true one. It was furnished by the advancing motion of the node, or that day's delay of the November shower every 70 years, which the old chronicles had supplied data for detecting. For this is a strictly measurable effect of gravitational disturbance by the various planets, the amount of which naturally depends upon the course pursued by the disturbed bodies. Here, the great mathematical resources of Professor Adams were brought to bear. By laborious processes of calculation, he ascertained that 4 out of Newton's 5 possible periods were entirely incompatible with the observed nodal displacement, while for the 5th, that of 33¼ years, a perfectly harmonious result was obtained. This was the last link in the chain of evidence proving that the November meteors, or Leonids, as they had by that time come to be called, revolve round the sun in a period of 33.27 years, in an ellipse spanning the vast gulf between the orbits of the Earth and Uranus, the group being so extended as to occupy nearly 3 years in defiling past the scene of terrestrial encounters. But before it was completed in March 1867, the subject had assumed a new aspect and importance. Professor Newton's prediction of a remarkable star shower in November 1866 was punctually fulfilled. This time, Europe served as the main target of the celestial projectiles, and observers were numerous and forewarned. The display, although according to Mr. Baxendale's memory inferior to that of 1833, was of extraordinary impressiveness. Dense crowds of meteors, equal in luster to the brightest stars, and some rivaling Venus at her best, darted from east to west across the sky with enormous apparent velocities, and with a certain determinateness of aim, as if let fly with a purpose and at some definite object. Nearly all left behind them trains of emerald green or clear blue light, which occasionally lasted many minutes before they shriveled and curled up out of sight. The maximum rush occurred a little after 1 o'clock on the morning of November 14th, when attempts to count were overpowered by frequency. But during a previous interval of 7 minutes 5 seconds, 4 observers at Mr. Bishop's observatory at Twickenham reckoned 514, and during an hour 1,120. Before daylight, the earth had fairly cut her way through the star-bearing stratum. The ethereal rockets had ceased to fly. This event brought the subject of shooting stars once more vividly to the notice of astronomers. Schiaparelli had, indeed, been already attracted by it. The results of his studies were made known in 4 remarkable letters addressed, before the close of the year 1866, to Father Secchi, and published in the Bollettino of the Roman Observatory. Their upshot was to show, in the first place, that meteors possess a real velocity considerably greater than that of the earth, and travel, accordingly, to enormously greater distances from the sun along tracks resembling those of comets in being very eccentric, in lying at all levels indifferently, and in being pursued in either direction. It was next inferred that comets and meteors equally have an origin foreign to the solar system, but are drawn into it temporarily by the sun's attraction, and occasionally fixed in it by the backward pull of some planet. But the crowning fact was reserved for the last. It was the astonishing one that the August meteors move in the same orbit with the bright comet of 1862, that the comet, in fact, is but a larger member of the family named Perseids, because their radiant point is situated in the constellation Perseus. This discovery was quickly capped by others of the same kind. Leverrier published, January 21st, 1867, Elements for the November Swarm, founded on the most recent and authentic observations, at once identified by Dr. C. F. W. Peters of Altona with Oppolzer's elements for Tempel's comet of 1866. A few days later, Schiaparelli, having recalculated the orbit of the meteors from improved data, arrived at the same conclusion, while Professor Weiss of Vienna pointed to the agreement between the orbits of a comet which had appeared in 1861 and of a star shower found to recur on April 20th, Lyraïds, as well as between those of Biela's comet and certain conspicuous meteors of November 28th. These instances do not seem to be exceptional. The number of known or suspected accordances of cometary tracks with meteor streams contained in a list drawn up in 1878 by Professor Alexander S. Herschel, who has made the subject peculiarly his own, amounts to 76, although the 4 first detected still remain the most conspicuous, and perhaps the only absolutely sure examples of a relation as significant as it was, to most astronomers, unexpected. There had indeed been anticipatory ideas, not that Kepler's comparison of shooting stars to minute comets, or Maskelyne's forza risultare che essi sono cometa, in a letter to the Abate Cesaris, December 12, 1774, need count for much. But Chladni, in 1819, considered both to be fragments or particles of the same primitive matter, irregularly scattered through space as nebulae, and Morstadt of Prague suggested about 1837 that the meteors of November might be dispersed atoms from the tail of Biela's comet, the path of which is cut across by the Earth near that epoch. Professor Kirkwood, however, by a luminous intuition, penetrated the whole secret so far as it has yet been made known. In an article published, or rather buried, in the Danville Quarterly Review for December 1861, he argued, from the observed division of Biela and other less noted instances of the same kind, that the sun exercises a divelent influence on the nuclei of comets, which may be presumed to continue its action until their corporate existence, so to speak, ends in complete pulverization. May not, he continued, our periodic meteors be the debris of ancient but now disintegrated comets whose matter has become distributed round their orbits? The gist of Schiaparelli's discovery could not be more clearly conveyed, for it must be borne in mind that with the ultimate destiny of comets' tails this had nothing to do. The tenuous matter composing them is, no doubt, permanently lost to the body from which it emanated, but science does not pretend to track its further wanderings through space. It can, however, state categorically that these will no longer be conducted along the paths forsaken under solar compulsion. From the central and probably solid parts of comets, on the other hand, are derived the granules by the swift passage of which our skies are seamed with periodic fires. It is certain that a loosely agglomerated mass, such as cometary nuclei most likely are, must gradually separate through the unequal action of gravity on its various parts, through, in short, solar tidal influence. Thenceforward, its fragments will revolve independently in parallel orbits, at first as a swarm, finally, when time has been given for the full effects of the lagging of the slower-moving particles to develop, as a closed ring. The first condition is still, more or less, that of the November meteors. Those of August have already arrived at the second. For this reason, Leverrier pronounced, in 1867, the Perseid to be of the older formation than the Leonid system. He even assigned a date at which the introduction of the last named bodies into their present orbit was probably effected through the influence of Uranus. In 126 A.D., a close approach must have taken place between the planet and the parent comet of the November stars, after which its regular returns to perihelion and the consequent process of its disintegration set in. Though not complete, it is already far advanced. The view that meteorites are the dust of decaying comets was now to be put to a definite test of prediction. Biela's comet had not been seen since its duplicate return in 1852, yet it had been carefully watched for with the best telescopes. Its path was accurately known. Every perturbation it could suffer was scrupulously taken into account. Under these circumstances, its repeated failure to come up to time might fairly be thought to imply a cessation from visible existence. Might it not, however, be possible that it would appear under another form? That a star shower might have sprung from and would commemorate its dissolution? End of Part 2, Chapter 10, Recent Comets, Part 1. Recording by Aaron Carlo in San Clemente, California.